So I wanted to make this video to introduce you to the idea of two-dimensional motion. A lot of the definitions that you see really haven't changed from chapter 3 when we did one-dimensional motion. But what we're doing is we're incorporating the idea of three-dimensional space in a vector nature. So we are utilizing the skills that we learned in chapter 2, which was vectors. So it's a combination of chapter 2 and chapter 3. So the first thing that I want to show is the picture that we see here, and it's defining how we look at the position vector when we have two or three-dimensional motion. Now, I know this picture is three-dimensional and I wrote two-dimensional here because most of the time we only deal with two dimensions at once. 3 dimensions is really not a big deal. You're just adding the z component, and everything that we go over today can be easily translated from the 2D nature that we're looking at to three-dimensional space. It's just a little easier most of the time to draw things and show them in two-dimensional space. So in the picture we have the XYZ space shown, and then you see you have a point where is the position or the present position of the object. And you also see the position vector r, which is a function of time. The idea is that point P, which designates the present position of the object, whatever it might be, is designated or determined by its x-coordinate, its y-coordinate, and its z-coordinate. And notice that it says that each one of those coordinates can depend on time. If we wanted to write the position vector then, the way that we would write it is we would indicate that there's an x component, and then we use the unit vector. Oops, I wrote y for some reason. It's x of t. X is a function of time, and the I unit vector, of course, indicates it's in the x direction. Then we have the y position, which can be a function of time, times the j component, and then z, which is a function of time, followed by the k unit vector, which is in the z direction. And so this is how we could write the position vector as a function of time. Each one of these components can depend on time in a different way, but then they would tell you what the x, y, and z components of the position is at a particular time. And so this is how we're going to show position in two or three-dimensional space. So let's get rid of that. So the next thing that we want to think about is the average velocity. The average velocity, of course, is defined. It's really no different than it was defined previously. It's just that now it can have more than one component. And so this, of course, is the displacement. Which is the change in the position. And so I chose this picture because it actually shows both the displacement vector and the average velocity vector. So in this picture right here, where you see actually the dotted line represents the path of the particle, whatever it might be. It doesn't really matter. Notice that, so that dotted line is just a line that's in three-dimensional space. Every point on that line has coordinates. It has an x, y, and z coordinate. And as you move along the path, of course, those coordinates change. And so what you can think about is that the path really represents the different values of x, y, and z at different points in time. So every point on that dotted line path actually represents a particular instant in time. Now, in this picture, they designated two positions, position 1 and position 2. The points on the path are designated as P1 and P2. So there's a lot I want you to look at in this picture. The first thing is the two position vectors, R1 and R2, are defined by, they go from the origin to the point on the path. So R1 goes from the origin to point P1. Position vector R2 goes from the origin to point P2. So R1 and R2 are two different position vectors at different times. And so if we wanted to find the displacement, which would be the first stage of finding the average velocity, then we would find the difference between those two vectors. And notice that's your delta R, is your displacement. Notice how it's drawn. It goes from R1 to R2. If you think about what that vector is trying to show, it should make sense that it goes from R1 to R2 because of the fact that it wants to sort of show where it started and where it's going, and that vector in that direction would be the proper notation or the proper way to draw it. Notice again that it's different from what we were looking at sort of graphically in class the other day for adding vectors. We are subtracting them, and these two vectors are drawn tail to tail. They're shown that way because they're literally drawn the way they should be to show where they always are drawn with respect to the origin. And then the delta R, the displacement vector. So that's something interesting because that allows us to calculate how far the particle has traveled. But it also goes into doing the calculation for the average velocity. Now let's look at this expression. The average velocity is a vector, which means it has a direction. It's the ratio of the displacement over the interval in time. Now the interval in time is a scalar quantity. Time does not have a direction. So the direction of the average velocity vector comes from the direction of the displacement vector. And you can see in this picture right here is the displacement vector, and then parallel to that is the average velocity vector. So the average velocity vector is parallel to the displacement vector. It won't necessarily be the same length because of the delta t. The time interval that you divide by will possibly change the length of the average velocity vector, but they will still be in the same direction, or it will be in the same direction as the displacement vector. And so that's important to see. One of the things that was shown in that other picture, was sort of how that average velocity vector was drawn relative to the path, but let's look at instantaneous velocity because this is what we really want to remember. So the definition of instantaneous velocity is, instead of looking at the change like the delta R over delta t, we're looking at the limit as delta t goes to 0 of delta R over delta t. And this ends up being the derivative of the position with respect to time. So that's a little bit hard to see, and I'm going to try to fix that. So the instantaneous velocity, or as we like to say, just velocity, is just the derivative of the position with respect to time. That is because the reason is that we're not looking at the change in the displacement over an interval of time, but we're letting that interval become very, very small because we want to know what's happening at a particular instant in time. And so the delta R over delta t changes to the derivative of R with respect to t. Another interesting thing that happens is that when you look at the paths, again, the dotted line is still the path of the particle. We've simplified things to the xy plane because it's just way easier to draw. But notice the velocity vector right here. It is tangent to the path, and that's something that's important to remember in these pictures. Anytime you're representing the path of a particle in two-dimensional space or three-dimensional space, the velocity vector is going to be tangent to the path. And so the two things that we looked at so far is that the average velocity is parallel to the displacement vector, which is probably not going to end up being tangent to the path because the velocity vector simply connects, or the displacement vector simply connects 2 points on the path. But as that delta time became very small, it would seem like it would be closer to what the tangent would be. But it's only when we make that time interval infinitesimally small by looking at instantaneous velocity that we can say with certainty that that vector will be tangent to the path. So I want to do an example problem of how we would use some of this information that we have so far in terms of how we would sort of translate this into doing a problem. So in this scenario, we're being given the position of a rover on Mars, and it's telling us how we can describe its x and y coordinates at any time. The first thing we're asked to do is to write the position vector r using the unit vector notation. So in general, r of t, the vector, would be given by an x component and a y component. And because we're just working with x and y components in this scenario, that's where we would stop. Now, I actually have expressions for how x and y depend on time, so I'm going to do a substitution here. And so what I've done is I've really just pulled these two expressions here and I've placed them here and here. And now I have a way that I can just write that position vector and how it depends on time. And notice that what I did is I did use my unit vector notation in order to be able to write them and say, you know, this is what the x component of this vector looks like, and this is what the y component of this vector looks like. So the next thing they ask us is, what is the position vector at t equals 2 seconds? And so, as you might suspect, all that I need to do to solve or to do this part of the problem is I let the time equal to anywhere I see it in these expressions. So what I've done is I've replaced the time by 2, and that's going to allow me to calculate the exact values for both the x and the y components when t is 2 seconds. And so what I do, I'm going to just skip some of the simplification or some of the intermediate steps and tell you what my x and y components would be. My x component ends up to be just 1, so I'm just going to write that as I hat. because it's implied that the coefficient of that is 1, and then the y component ends up to be 2.2. And so that's how I write the position vector when the value of time is 2 seconds. The next thing I want to do is it asks me to find the displacement vector between t equals 0 and t equals 2 seconds. So in a sense, what I have to think about is what is r at t equals 0. And so putting in t equals 0 for the x and y coordinates, I would say that the x component would be 2I, but the y component, because both of those terms in the y expression involve time, they would both be 0, so I wouldn't get any values for that. And so when I calculate, I'm going to move over here to have more room, the delta r, which is r at t equals 2 minus the r at t equals 0. And I want to make sure you can see that. We actually already know what those two position vectors are, and so I'm going to have it I plus 2.2j minus 2I. And so this was the position vector when t equals 2 seconds, and this is when it equals 0 seconds. And then I subtract these two, and so I find that the displacement vector, which I was asked to find, is minus I plus 2.2j. So that is my displacement vector. My average velocity vector between 0 and 2 seconds, you can see that all this is building on one part builds on the other. My average velocity is simply found by taking that displacement and divide by the delta time. So I'm just going to take the expression that I just found, and my delta time is 2 minus 0, which is just 2. And then I'm going to say that my average velocity is minus a half plus 1.1 j. And so that's what my average velocity is. Finally, the last thing that I'm asked to find is the instantaneous velocity at 2 seconds. Now, what I have to remember is, what is the difference between average velocity and instantaneous velocity? This is something that some of you had some trouble with in the first assessment, sort of differentiating between how do I find average velocity versus instantaneous velocity. Remember that instantaneous velocity is just the derivative of position with respect to time, which would really mean that for the x component, I would be taking the derivative of x with respect to time, and for the y component, I would be taking the derivative of y with respect to time. To simplify this, it's simply the instantaneous velocity term has two components, an x component of its velocity and a y component of its velocity. And once again, the x component of velocity is the derivative of x with respect to time. The y component of velocity is the derivative of y with respect to time. In order to find the expression that we use for this particular problem, I need to take the derivative of these expressions right here with respect to time to write a general expression for velocity as a function of time. The general expression for velocity as a function of time is going to be minus 0.25 times 2 times t is the x component, and in the y component it's going to be 1 plus 3 times 0.025 times t squared, and that's the y component. So I'll just step away that you can see that. I should have bigger brackets around all that. And so let's just simplify that a little bit. And so the velocity vector as a function of time is minus 0.5t in the x direction, and then 1 plus 0.075 t squared. Oops, sorry about that. I can't see those on when I'm writing here. So I'm going to just go down here and try to squeeze it in. Velocity as a function of time is minus 0.5 t in the x direction. These pens are giving me a lot of trouble. And then 1 plus 0.075 t squared in the j direction. So hopefully you can see most of that. That's the velocity vector. If I let time equals 2, substitute in for that, and my end result is going to be minus I plus 1.3j is my velocity vector for velocity at t equals 2. So this is the answer to the first question right here. The second part is found right here for the two position vectors. The displacement vector is found here. The average velocity vector is found here. And finally, the instantaneous velocity vector or answer is found right here. I know, it's kind of messy, but there was a lot of work. I wanted to show you all the steps. So we're going to erase here so we can just talk really quickly about acceleration. So the average acceleration, as you know, is by definition the change in the velocity over the change in time. And so in this picture, they're trying to show you how the fact that you can see that, again, dotted line is the path. The two velocity vectors at the two times that we've chosen, time 1 and time 2, are drawn so that they are tangent to the path, which is what we learned. Those velocity vectors, of course, are instantaneous velocity vectors. We would use instantaneous velocity values when we would find the average acceleration. Now, what they did right here is they brought the two velocity vectors together, sort of moved them in space. They still have the correct orientation or direction, so that we could show the change in velocity. And what I want you to take note of right here is that change in velocity, of course, is going to be determining the direction of the average acceleration. And you can see for sure here that the direction of the average the average acceleration, which is given by the change in velocity, is not parallel to the path. Part of the reason, and we'll start to understand that as we talk more about different paths as we go through this chapter, is that when the path is curved, it does require a change in velocity that sort of goes in towards the center of that curve, and that also will then cause an acceleration because of the change in the direction, and that will be its direction of that acceleration. So it's just important to note that while the instantaneous velocity is tangent to the path, the average acceleration, and it will also turn out the instantaneous acceleration, do not have to have some particular orientation relative to the path. And they would only be tangent to the path in a very special situation. This is a nice picture just illustrating for us how the average velocity and the average acceleration are parallel to each other, and also how they are oriented relative to the path. And finally, we're going to finish up by thinking about just instantaneous acceleration, which we can also call acceleration. And so what we're going to say is the acceleration vector is just going to be the limit as delta t goes to 0 of delta v over delta t, which by definition is the derivative of velocity with respect to time. Seems to make sense. And so you can see that as we go from position to velocity to acceleration, the way that we do is by finding derivatives of those expressions. You can see that the velocity vector, just to remind you, is always going to be tangent to the particle's path, but the instantaneous acceleration vector does not have to be tangent to the path. So this concludes this video. I wanted to just give you a brief introduction of how we apply our existing knowledge about position, displacement, average velocity, instantaneous velocity, acceleration, etc., to a two-dimensional or a three-dimensional space. The definitions are the same, but as you saw, we're also using, at some points, unit vectors and vector notation because we need to do that when we have more than one dimension.